SwayamPrabha. Digital India. Educated India.
In this lecture, we will continue our discussion on generation of forces and moments on an aircraft. So, the concepts that we will cover include integration of pressure and shear stress to obtain forces and moments. We will choose an airfoil to do this exercise. Then we will look at relations between different force components, and we will look at the relation with angle of attack. And finally, we will look at some non-dimensional coefficients for forces, moments, pressure and skin friction, and as they apply for 2D and 3D bodies. Here are the key points. We will briefly recapitulate this diagram, which we have seen in an earlier lecture, where you can see that there is an airfoil section and it is facing the airstream u infinity at an angle of attack alpha. It has a leading edge and a trailing edge, and the straight line which connects the 2 points on the airfoil is the chord. So, the airfoil shape is formed by having a certain amount of thickness disposed about the chord. This is basically a 2-dimensional geometry, which means that if you look at the third direction, which is orthogonal to this plane, that is the z direction, there would be no change in the geometry of this body. If you were to look at the third direction, you would see this airfoil section getting extruded, and thereby you could look at this small element on the airfoil surface as getting extruded in the third direction. We will call this small element ds. On that small element, there is pressure which is acting normally, and remember that pressure acts into the surface. There is also shear stress which acts tangentially to the surface, and it has a tugging effect on the body, because it plays the role of friction which opposes the motion. If the flow was not existing here, you would have atmospheric pressure acting on every portion of the airfoil. The moment there is a flow around this body, the pressure and the skin friction develops and changes from the atmospheric pressure. There could be regions on this airfoil where the pressure is well below the atmosphere. Now, you are interested to look at how the pressure distribution and the shear stress distribution on the airfoil finally leads to the formation of forces and moments. Remember that aerodynamic forces and moments which are created on a body are produced purely due to these two effects. No matter how complex the body shape is, it is always these two distributions which matter. Now, we are looking at the net effect of the pressure distribution and the shear stress distribution, and we find that the net effect happens to be an aerodynamic force R and a moment. We call this as the pitching moment. It is one of the 3 moments which we will discuss in due course. So, here the pitching moment is shown as acting clockwise, and here is the resultant force R. You can resolve the resultant force into 2 possible components. One way of resolving it is the force components which are orthogonal to the chord and parallel to the chord. So, that forms the normal and the axial force. There is another way of resolving are the two force components lift and drag, which happen to be perpendicular to the free stream and parallel to the free stream. We find that there is a relation between the normal and axial forces and the lift and drag. If you write down the relations, you will be very easily able to derive this, that lift and drag would be represented as a function of normal force, axial force and angle of attack using these equations. So, you can take it up as a homework problem. It is very interesting to see that when alpha is small, lift is nearly equal to the normal force and the drag is nearly equal to the axial force. Now, we are going to look at the integration of pressure and shear stress distributions over the airfoil, how it ends up producing the normal and axial forces as well as the pitching moment. And then of course, by using the two equations that we just saw in the previous slide, we can derive the equations for the lift and drag forces as well. We are also interested to look at some non-dimensional or dimensionless coefficients concerning forces, moments, additionally pressure and skin friction, and how the nomenclature would be used if it is a two-dimensional body or it is a three-dimensional body. So, examples of 2D and 3D bodies would be airfoil and wing. Now, let us do a small exercise whereby we are able to find out the integrated effect of the pressure and shear stress distribution. For that, let us begin by having a small sketch of the airfoil, and as we said that the leading edge of the airfoil lies at the origin of the coordinate system. The trailing edge is at a distance c from the leading edge. And of course, we are going to look at different points on the airfoil surface and how the pressure and the shear stress acting at that point finally sums up giving us the forces, but it is important for us to select a few of them carefully. On the upper surface, we will define 2 points A dash and A, where A dash is near to the leading edge and where the airfoil is sloping upwards, while the A point is here in a region nearer to the trailing edge and where the airfoil surface slopes downwards. Similarly, on the bottom surface, we will choose 2 points B and B dash, where similar things happen. Now, we are going to use two distances following the surface. On the upper surface, the distance that we measure by following the surface will be called as SU, and on the lower surface, the corresponding distance will be called as SL. Let us look at some conventions for sign. It is very important to follow a sign convention for theta, where theta is the angle between the normal on the surface, or rather normal to the chord, and the direction of the pressure. So, I will draw it a little larger later on to show the details. So, that is the angle theta, and the sign convention for theta would be that it is positive when measured clockwise from the vertical line which is this dotted line, to the direction of P. This is considered to be positive, and horizontal line to the direction of tau. This convention is very important to be remembered. Now, let us look at these 2 points A and A dash, like we mentioned on the upper surface. So, we are looking at the upper surface in a more magnified manner now. You have one point A dash here, another point A. As we said earlier, the pressure always acts normal and into the surface. We will hatch the surface. Now, this is the vertical, this is the horizontal, and we see that in order to reach the P direction, we are going the opposite way to clockwise, and therefore, this is negative theta. Similarly, we have gone counterclockwise from the horizontal to reach tau. So, this is also negative theta. Therefore, for this calculation, if you were to use sin theta, cos theta as part of the calculation, then you have to remember that sin theta will be negative and cos theta will be positive. These terms will come later, that is why we are worrying about the sign. For the point A, let us see how it works out. So, this is pressure, this is shear stress, and the horizontal and vertical lines are dotted. You are moving clockwise for both in order to reach the directions from vertical and horizontal. Therefore, these are positive by the convention that we are following. Consequently, sin theta and cos theta terms will be positive, both will be positive. Remember that the aerodynamic force acts over a certain length here. So, we will have to define a small element, we will call it ds. And if you were to define an area over which the forces were acting, then what you have to do is take the length of this element and multiply it by the span, which is essentially along the z direction. We would do the calculations by assuming unit span. Unit span. Therefore, the forces that we work out will work out as forces per unit span or moment per unit span and so on. Let us write down the elemental normal force expression, and then we will check whether it works equally well for both points A and A dash on the upper surface. So, we are writing an expression for the normal force as it works on this small element ds and on the upper surface. Notice that we are writing a subscript u for pressure on the upper surface and also for tau. We will call this equation 1. Similarly, let us write an equation for the axial force which is acting on the elemental area. Let us call this equation number 2. Now, coming to the signs of the different terms which we find over here. Let us give them some names for convenience. We will call this as NUP, that means the normal force on upper surface due to pressure, normal force upper surface due to shear stress, and the two terms in the axial force as AUP and AU tau. Okay. So, let us see how the signs of these different terms work out. We will make a small table where we mark the forces on top and we look at the 2 points A dash and A, and we try to figure out what the signs of these terms are. You will see that they work out like this. And if you watch the diagram carefully, these are giving the consistent signs of the different terms. Therefore, the expression works equally well for the 2 points A and A dash. Similarly, you can go to the bottom surface or the lower surface and identify 2 points on the lower surface, one closer to the leading edge and one closer to the trailing edge. So, this is the lower surface of the airfoil. So, let us name this point as B, which is closer to the leading edge, this as B dash, which is closer to the trailing edge. You would notice that for points A and B, the theta is positive, while for A dash and B dash, the theta turns out to be negative. Once we draw the diagrams, it will become clear to you for the lower surface also. So, we have drawn the vertical and the horizontal lines. As you can see, we move clockwise from the vertical to reach the pressure direction, and we again move clockwise from the horizontal direction to reach the tau direction. So, this is going to give me positive sin theta and cos theta. So, both are positive. While here, let us try to see what happens. You can see that you have to travel counterclockwise. Therefore, what happens is sin theta becomes negative, while cos theta remains positive. We have to be very careful about these signs. Now, let us write down the elemental normal force and elemental axial force for the lower surface points. So, the elemental normal force So, we have these two equations for elemental normal and axial forces, where the pressure on the lower surface is indicated by P L, shear stress by tau L, and pressure and shear stress they work on elemental area, where though it shows up as a length, as we mentioned earlier, that it takes care of the area aspect by considering unit span. So, what you get out of this essentially is an area. So, dimensionally they are consistent. And as you can understand, the sin theta cos theta terms based on the sign convention work appropriately when we look at the direction of theta, that means whether it is positive or negative. Let us form that table which we did for the upper surface here also. So, the normal force has two sources, pressure and tau, so does the axial force. I hope from the equations 3 and 4 you would be able to identify the components now. We mark the points B and B dash, and we will find how the sign of these different components work out. Note that the normal force, when we look at it, is pointing towards the positive y direction. That is the direction of the normal force. The axial force is pointing towards the positive x direction. That is how we are looking at positive values of normal and axial forces. Now that we have derived expressions for elemental forces, we can integrate them. So, we integrate the elemental forces from leading edge to trailing edge of the airfoil. So, we can write an expression now for the normal force that takes care of both the upper surface as well as lower surface contributions. So, if you know the geometry of the body, then point to point you have information about the theta, and you also know the location of the points as a function of the running coordinates SU and SL. And remember that these forces are essentially per unit span, that is for a two-dimensional body. In both the equations, there are contributions from the upper and lower surface. We will call these equations as 5 and 6. Finally, once you have got the forces per unit span N and A, you are going to use the angle of attack to express the lift and drag forces. We know about these equations before, but we will write them again over here for the sake of completeness. Now comes the issue of aerodynamic moment. And the one that we are discussing over here happens to be pitching moment. There are another two types of moments which we will discuss later, which are called as rolling and yawing moment. We are going to take the moment about the leading edge, and by convention we will assume that the moment is positive if it tends to increase the alpha, which is called as pitch up. So, the convention that we are going to follow is that moment which can increase the alpha, that means cause a so called pitch up, will be considered as positive. So, let us say you are indicating such a moment. So, this is your leading edge about which the moment is being calculated. So, you show it like this, that is a pitch up moment, and that is a positive moment. Obviously, a moment which decreases alpha or leads to a pitch down would be considered negative, and that would be opposite in nature. Counterclockwise. How do we calculate the moment? Well, we have to incorporate a moment arm in addition to the force expressions. So, the moment arm comes in here. And what we are doing is we are using the moment arms x and y to compute the effects on the upper and lower surface. We will draw a small diagram at the bottom to explain what we mean by those moment arms. So, let us suppose this is your axis system. So, the chord is of course along the x axis, and you are looking at some portion of the upper surface. Let us say this is a point A, and you are looking at its coordinates. So, you can define its coordinates as say x A and y A. So, when you are calculating the elemental moment which acts due to the pressure and shear stress distribution on that small element d s centered about point A, then you are going to use these coordinates as the moment arms here. Likewise, it is done for all remaining elements on the airfoil surface, and then the total effect is integrated in order to get the total moment. So, the total moment about the leading edge, it is very important that we mention about what point we are calculating it. So, it comes out like this. This would be a minus. So, this is the contribution of the upper surface, and the other is the contribution of the lower surface. This is how it will work out. As long as you know the values or the distributions of pu, tau u, pl, tau l, x, y, theta, these values are available to you either from theory or from experiment, you can integrate these expressions, and therefore, you can obtain the forces and the moments. Now, let us look at whether we can non-dimensionalize these forces and moments. Actually, we can, and for 3-dimensional bodies, let us say if you are looking at a wing, then the plan view of a wing may look like this, where you are not considering other elements of the aircraft like fuselage and so on. What you see from top is called as the planform area, and the flow comes in from upstream and meets the wing like this. If you take a cross section of this wing at some location, then what you see is an airfoil section. This is where you see the airfoil section. Now, if you had a wing where the sectional geometry did not change along the span, then that would be a 2-dimensional wing, so to say, because its section does not change along the third direction. However, here it does, and it also has finite extent, it has tips, it has finite span. These are the two tips, and what you have in between is the span, and it also has a chord which varies along span. So, you can actually take some kind of a average of the chord as it varies along the span and define something like a mean chord. As long as we deal with 3-dimensional bodies, the coefficients that we generate by non-dimensionalizing the forces and moments are going to be indicated by capital letters. So, let us say we non-dimensionalize the lift and we represent it as a coefficient. So, that coefficient will be called as capital C suffix L. For drag, it would be capital C suffix D and so on. However, if you were doing it for a two-dimensional body, which essentially has infinite span, and you are calculating the lift of that body and indicating it using a non-dimensional coefficient, that would be represented as small cl, the drag as small cd and so on. In order to define these coefficients, we would like to recall about the free stream dynamic pressure, which we discussed in an earlier lecture. So, let us introduce the definition of the free stream dynamic pressure. And with the help of that, as well as the reference area, which is the wing area, more appropriately as wing planform area, and a reference length, which in the case of the wing could be a mean chord, which can define all the different coefficients. So, lift would be defined, lift coefficient will be defined as L by q infinity s, drag coefficient as d by q infinity s, normal force as n by q infinity s, similarly axial. We have to be careful about moment, because moment has to be non-dimensionalized by including an additional length element here, because the forces have been multiplied by appropriate length scales in order to generate the moments. So, we have discussed about all these points which we planned to. We conclude this lecture by looking at the main points. So, in this lecture, we looked at integration of pressure and shear stress distribution on an airfoil and consequent normal force, axial force and pitching moment generation. We looked at lift and drag forces being expressed as a function of normal force, axial force and angle of attack, non-dimensional coefficients and their nomenclature for 3D and 2D bodies, and the normal force, axial force and pitching moment coefficients can be expressed in terms of pressure coefficient, skin friction coefficient and surface geometry, the slopes and the xy coordinates. This part we will discuss in further detail in the next lecture. Thank you.